All right. Welcome everyone to yet another Cosmos webinar. My name is Jonas Rosling. I'm the Director of Community here. Thank you everyone for joining here today. We have a fantastic webinar from some fantastic individuals from Clemson University. We got Becky Ligon, we got Carl Ehrett, Scott Groel, Thomas Wright, and Krystal who will talk about the immense Palmetto 2 cluster, talk about the infrastructure, talk about the workloads that are running on there, and also Krystal is going to dive into her results actually stemming from the workloads running there. So this is going to be super interesting. If you have any questions throughout the webinar, please put them in the Q&A, and I'll make sure that we handle those throughout the webinar and also at the end of the webinar. So again, if you have any questions, please put them in the Q&A. If you have other chat things, of course, put them in the chat. That's perfectly fine. And with that, I'm going to hand it over to you. I think Scott is going to lead us off here.
Yep. Hello, everyone. My name is Scott Groel. I'm the Executive Director of Research Computing and Data Infrastructure at Clemson. So a little bit about us and what we've been doing. We've been doing research computing centrally managed through our IT organization, CCIT, since 2007. It was an initiative brought through by our then CIO to eliminate closet clusters and bring a centrally managed resource that was democratized to the whole community at Clemson. We've added on to it, year over year. So it's an extremely heterogeneous environment. And this about 2021, 2022, we received some funds from the university to refresh our infrastructure post-COVID. So we're going to dive into a little bit about our cluster and what we did with those funds and kind of how we set up our model and our storage. So we're going to go over the ecosystem first, kind of what the overall storage layout looks like for our system. We moved from a compute-centric model to a data-centric model. We wanted to make data more accessible to users. Right now, we have VAST that kind of sits in the center. We have users that can directly interface with the system on campus, any campus network, so wireless, VPN, wired connections, and any of our extension offices that are through the entire state of South Carolina. They can interface directly with the VAST system and mount their storage spaces via SMB. We provide that's those same storage spaces to Palmetto 2, which is our HPC environment over InfiniBand, leveraging NFS over RDMA. We use that same protocol stack for data transfer nodes for Globus, which then speaks Ethernet out to the world, including high-speed connections over Internet 2. And then for backup, we're using ZFS as a data catalog and movement tool, and we're moving data sets down to ZFS for backup, and we're bringing online a secondary system for disaster recovery that's going to be located in our tertiary data center. That's just going to be a mirrored copy, and we're going to be leveraging ZFS send receive to mirror those systems. So really, we kind of built this to protect user data and make it easier and more accessible to researchers, where storage wasn't just tied to the HPC system, but now any researcher that may not even be using HPC can now use a centrally managed system to host their data. So the configuration that we have for the VAST system today consists of 3 C boxes, 8 of them speaking InfiniBand and 4 on Ethernet, and 3 D boxes, 1 675 and 2 1350s. We originally started with 1 C box and 1 D box that was kind of a proof of concept host, and we decided to expand upon that after we got some experience with it. We really liked it and expanded out another couple C boxes and the 2 1350 D boxes. For network connectivity on these are connected to redundant switch pairs. So InfiniBand has 2 HDR 100 connections. Each C node has 1 connection back to individual switches, and then same for Ethernet. We're using 50 gig there. When we first deployed the system, we actually were dual stacking, so we only had 2 C boxes.
and we're doing InfiniBand and Ethernet on each C node. It was a bit challenging at first. We ran into some issues with that. Mainly, we had to get the configuration up through the API and modifying some scripts on the VAS system itself. This was later resolved and was functional in the VMS. But we still ran into some issues. We were hoping, by using 100 gig and 50 gig, the PCI Express Gen 3 C nodes that we had, we were hoping to avoid contention on the PCI Express bus. But we still ran into issues when we saturated the IB links where it would drop Ethernet traffic. So that was why we decided to add another C box and then split them to protocol specific. That allowed us to get some more quality of service on Ethernet. So as I mentioned, for user connectivity, we have users that connect directly to the system via SMB. So we have users that can purchase storage through us directly. We offer 1 terabyte for free for all faculty, and then we sell storage based on per terabyte per month basis, and they can buy out multiple months up front. And then that same storage space is available on any of our resources on the back end. We only allow users to connect via SMB, but if they're for university managed systems, such as computer labs, we do allow supporting via NFS. This is just to ensure that we don't have users spoofing UIDs and GIDs. It's a way to protect. When it's university managed, we can control that. We have one lab on campus that's mounting NFS that's doing digital production arts on the system on campus. The VAS system is actually located off campus in our main data center that's about 20 minutes outside. So we have multiple fiber pads that run back there. Connectivity back to our HPC and DTN nodes is over HDR 100 InfiniBand. So that's our high-speed connectivity. We also control some of the access to the VAS system through network firewalls and whatnot on the Ethernet side. That's really to just protect incoming connectivity from campus and to really ensure that we restrict NFS traffic to only specific hosts that we want. So back up in DR, like I said, we were using Starfish as a data catalog and data mover. We have data that's tagged to be backed up to our ZFS storage system. So right now we have Scratch, home directories, and project space are all hosted on our VAST. We refer to our VAST as the Indigo Data Lake. So if I interchange terms, I'm sorry that we do reference it by Indigo quite a bit. So, we don't necessarily want to back up Scratch. I mean, it's our Scratch base. So we use the tagging feature to ensure that we only back up the data sets that we want. And we do have snapshots on those backups as well. So in conjunction with the snapshots that we have on the VAST, we also have snapshots on the backup system. And those are generally longer term snapshots. And we are building out a separate DR system that's hosted in our secondary data center. That's just going to be really cold. Critical event happens in the data center. It's more to ensure that we have a copy of the data somewhere. But that's, our current environment. To get from our backup system, which is located in the primary data center, to the secondary, we're actually using a homegrown product called Zetanite, which helps facilitate some of the management of ZFS file systems. So I'm going to dive into a little bit of compute resources, touching on both HPC and AI. So Palmetto 2 is our new HPC system. It was launched in May of 2024. It's really a continuation of Palmetto 1. The difference being we made substantial changes to Palmetto 1. We changed the job scheduler. We dropped out a lot of hardware, added a lot of new compute capacity. We have a lot of new policies and procedures, feature sets. It was a major change in how we were running HPC at Clemson. So we decided to make a change in the name just to drive home to users that the way that they use HPC at Clemson was going to be a bit different on this system. It is a top 500 system at 3.01 petaflops, number 352 as of the November
list. It is extremely heterogeneous. We have 1,000 compute nodes, 1,500 GPUs in those systems of all various types. I mean, we have K20s, K40s, P100s, V100s, A100s, H100s, you name it, it's probably in there. Been doing NVIDIA GPU compute for a long time. And we have several generations of InfiniBand that are connected through. Our primary fabric that's servicing all of our new infrastructure is HDR at the top end. It's a leaf spine topology with HDR 100 to the compute nodes, but we've started adding some NDR capacity as well. Our last edition of CPU compute, which featured AMD EPYC Genoa 9654s with 96 cores per socket. We bumped to NDR 200 for high density 200 gig connections, and we're looking at refreshing that fabric shortly to add NDR at the spine level to give us additional capacity. So 1,500 GPUs, 47,000 CPU cores, InfiniBand interconnect. We are tracking RDMA over converged Ethernet, but the challenge for us is since we build on this system year over year, it's very difficult for us to make a change on the interconnect fabric because then it limits the scalability on nodes because there's only a smaller subset that are using that new interconnect. So we have to try and time it with, if we were going to make a change to when we make a substantial investment in infrastructure. Speaking specifically of AI resources on the cluster, we have right now it's about 56 H100 GPUs in a small dedicated highly interconnected cluster. We chose the Dell XE9680 chassis. Each one has 8 H100 80 gig GPUs. And we're interconnecting those nodes with 8 NDR InfiniBand connections. That's 3.2 terabits of network communication per host. We also have an additional HDR interconnect just for storage traffic. We're doing some testing with that right now, and we're looking at GPU direct and how we can, and looking at how that's driving the storage, and we're looking at expanding that capacity to help feed these GPU systems. Speaking of other resources that are in the cluster, we have 220 A100 GPUs and 250 V100 GPUs. These are all mostly PCI Express based, but they're really good for smaller jobs, and we can also scale up. But we're using this AI cluster for really our larger AI machine learning workloads. And it is growing. We're anticipating at least one more 9680 coming in, probably going to be H200 based, and we have some possible options in the future to expand this beyond that as well. So access to our resources is highly democratized. All Clemson faculty and students can access Palmetto and our AI resources. We only require that students have a faculty member that sponsors those accounts. This is just for accountability and tracking what people are doing on the cluster a little bit more easily from the top level. It is a condominium style, so faculty can purchase resources to be added to the cluster, and if they do so, they get priority access to those resources as well as the ability to have external collaborators. This means that a faculty member at another institution can get an account on Palmetto and run it using either the storage they purchased on the VAST, if they have access to that, as well as run compute jobs on the nodes that they own. So that's a top level overview of kind of our HPC environment, and be happy to answer some questions if anyone has any.
So I have a few questions here. The first one is, of course, what does the name Palmetto come from, and how did you choose it?
Palmetto is the state tree, and it was decided long before I got to Clemson, so we continued it on with Palmetto 2.
That makes sense. You mentioned the NVIDIA infrastructure and the was it 1,500 plus GPUs of various types. Are you standardizing on NVIDIA, or are you using various manufacturers?
We've had some other ones here and there. We've been playing around a little bit with an AMD Instinct system, and we have had like Intel Xeon Phi based cards and things in the past. But we've been using NVIDIA for a long time, and one of the nice things about it is the driver stack is very. It can be cumbersome at times, but at least it's somewhat stable, and it does support multiple generations of a product. We have gotten burned in the past buying other products for support to be dropped relatively quickly after deployment. Yeah, we've been running NVIDIA for a long time. We're always evaluating other options, but a lot of it comes down to the software ecosystem. We don't do much software development. We're much consumers of pre-built software packages and whatnot. We leverage SPAC and what to build modules, so that can automate a lot of the processes. But in terms of actually supporting it and helping users troubleshoot, that's why we've kind of stuck to one vendor right now. But we are constantly evaluating and looking at alternatives.
That makes sense. Tailing off of that, so you talked about the condo model where faculty can purchase resources to add to the cluster. How do you handle that? Do you have specific standards that they need to follow, so you add the same thing, or how does that work?
Yeah. So typically we'll set up a consultation session with them. So they'll come in, we'll go over the code that they're planning on running, their workload. And that way we can make sure that, if someone has a job that's CPU based, we don't want them to go out and buy a GPU node. So we want to make sure that we tailor the equipment purchase to what's going to best benefit them and their workload. But we do have several standardized configurations that we have for users to select from. L40S, H100, CPU compute, large memory. But if what they're looking for doesn't fit that specific model, or say their budget doesn't fit with those existing models, we will work with them to get other systems or other configurations that'll work for them. The way we have base system requirements, and that's the InfiniBand connectivity, 25 gig Ethernet, and out of band management, and then we can generally work around the rest of the system. We typically create a feature, a set of features in Slurm, and that's how we can kind of partition things. And so we do have like a bunch of machines that are a single node of a specific type, but we push those down in priority. So that way jobs will typically fill in where we have large contiguous sets of hardware. And then, if there's additional capacity or someone's requesting those specific resources, then those jobs fall down to those nodes.
Fantastic. Thank you. I'll leave the rest of the questions for later.
All right, I'll put my slides on. Good. So, hello everyone. I am Dr. Carl Ehrett. I'm the Director of Applied Machine Learning in Clemson's Computing and IT Research Computing and Data Group. And what I am going to talk about today is just some of the things that are happening in the AI space at Clemson. So, first of all, just a look at some of the programs and institutes that we have that are focused on AI at Clemson. First of all, we have the AI Rise Institute. This is the AI Research Institute for Science and Engineering. So they are very focused on general promotion of AI research, also on education and workforce development and industry collaboration. And among their focus areas, a top goal of the Institute is to position Clemson as a leader in advanced manufacturing and material science. Clemson researchers are doing a lot of really innovative things with AI in the material science space. But in addition to that, also bio and medical informatics AI for cyber infrastructure, and AI for intelligent transportation, including, for example, AI for self-driving automobiles. AI Rise is led by a coalition of researchers from a variety of places in the university. So our School of Computing and also Electrical and Computer Engineering, as well as the Department of Automotive Engineering. And AI Rise researchers are doing a dizzying array of different kinds of AI-related research. So this spans from, for example, using AI to protect self-driving vehicles from cyber attacks, to also using AI on an assembly line to inspect vehicles for defects as they travel down the assembly line using, for example, computer vision methods. Using natural language processing AI methods to safeguard reputations on social media and also to detect cyberbullying and other forms of online harassment. And even using AI for things such as diagnosing Alzheimer's disease earlier than previously possible. And this is just a sampling of the different kinds of projects that AI Rise researchers work on. In addition to that, we have, as a separate institution, the Clemson MUSC AI Hub. And this grows out of a collaboration between the two universities where we have a joint master's and PhD program in biomedical data science and informatics. And so as an outgrowth of that, we have this AI hub that focuses on promoting research collaborations between the two institutions, specifically focused on biomedical AI. And so both of those institutes are broadly focused mostly on research, but there's also a lot happening, obviously, in the education and workforce development areas in AI at Clemson. So, of course, there are traditional courses in all kinds of departments at Clemson that have to do with AI, not just the School of Computing, but also the School of Mathematical and Statistical Sciences and Electrical and Computer Engineering and other departments. But in addition to traditional classes, we have various ways to promote experiential learning with respect to AI and related topics. So one example of that would be the Watt AI program. So this is a program where housed in Clemson's Watt Family Innovation Center, where researchers from any academic discipline in Clemson who might be interested in applying AI and machine learning to the research, but maybe they themselves don't have the requisite background to go it alone. They can come and consult with Watt AI researchers about just the possibilities in the AI space. What can AI do? What can't AI do? And how does AI potentially connect to their specific research domain? And those consultations have their own, value, and sometimes they're an end in themselves, and the researcher can go on their merry way and independently apply AI and machine learning methods afterwards. But in many cases, those consultations develop into ongoing collaborations, usually under the umbrella of Clemson's Creative Inquiry program. And this is a program, Creative Inquiry at Clemson is much larger than just the focus on AI. Watt AI is one example of a creative inquiry at Clemson, and it's Clemson's way of promoting undergraduate research and experiential learning. So students who take part in a creative inquiry are approaching problems not just in a classroom setting where it's a static problem that has a known solution and a known method that you should use to approach it. They're grappling with real research problems where nobody knows how to solve them and nobody knows what the answer is, because if anybody did know, then it would not be a real research problem. And so students who are interested in getting that kind of real world experience, specifically in the area of AI and machine learning and learning about these tools and using these tools, they can apply to join the Watt AI program. If they're selected, then they're placed on a small team, just like 3 to 5 students. And so that small team will work with one of the Watt AI researchers and with the faculty member from whatever specific discipline, the faculty member who was interested to apply AI and machine learning to their own research. And so it's a great way for students to really get their hands into some real research. In addition to that, we have also now new, quite recently, the Clemson Board of Trustees approved a new Clemson University Center for Human AI Interaction, Collaboration, and Teaming. So this is going to be a center headed by Dr. Nathan McNeese that is going to focus on research about how humans and AI can most productively collaborate, how AI can be most productively integrated into workflows, and how to mitigate any of the potential negative outcomes from that change. So this is just a few of the AI-related initiatives happening at Clemson these days. And supporting all of these and supporting the rest of the Clemson community with respect to compute, we have the organization that I and Scott and Becky are a part of, the Research Computing and Data Group in Clemson Computing and IT. So we support research, education, innovation at Clemson related to computing in any way we can. And oftentimes, of course, that support means traditional tech support, but it also includes things like advanced training. So we provide, for example, workshops that can be as general as Introduction to Linux or a general introduction to AI and machine learning topics. Or on the other end, it can be as specific as building a large language model from scratch in PyTorch. And so we really try to figure out where are the researchers' needs, what are the gaps in researchers' knowledge that are holding them back from making as much progress as they could. And where appropriate, we try to develop training and resources to fill those gaps. So in addition to workshops like that, we do guest classroom lectures, we do one-on-one consultations with researchers, we provide project support and things like grant proposal review and even help develop grant proposals related to AI and machine learning and other topics having to do with compute at Clemson. So that covers what I wanted to talk about today. We have with us one of those Clemson researchers. Krystal Leo is a PhD candidate in industrial engineering who is using Clemson compute resources to do some really interesting things in the AI space. So I'm going to be around. I'm going to be in the chat. If anybody has questions from me, I can talk to you there, but otherwise I will go ahead and turn it over to Krystal.
Thank you so much, Eric.
Mm-hmm.
So good afternoon, everyone. My name is Krystal. I'm from the Department of Industrial Engineering at Clemson University. And I'm a PhD student co-advised by Dr. Hegde and Dr. Ehrett. Today, I'm very honored to present my research using the Palmetto 2 high-performance cluster infrastructure to explore the research topic I'm really fascinated with. And to be honest, without the kind of hope from the Palmetto cluster, as well as the supercomputing power, I couldn't just make my research idea a reality. So without being said, I'm really very super excited to introduce everyone about the research results that I got from the Palmetto 2. The topic I'm talking about is large language models for proactive learning in healthcare, or comparative study of traditional incident reporting versus the resilience engineering approaches. So here is the agenda for today, but first I'll walk you through the introduction, a little bit background about the proposed approach, and the resource analysis, and limitation and future work of this research with the continual improvements from the AI machine like computing abilities, and also wrap up with our study conclusion. So first, introduction. For these research ideas is we learned that in the previous study in healthcare, the patient safety event is a very critical concern in healthcare systems. As you can see, there are like maybe patient 4 and surgical site infection, adverse drug events, or missing communication that happens like during the healthcare activities. But like these are the common patients instance. But according to the American Hospital Association, like about 100,000 people died per year just due to these very medical events that shouldn't be happening in the United States, and also have huge economic loss. But as such, this is very essential like for us to find ways to identify these safety events, like learn from them to improve patient safety as well as overall system performance in healthcare process. And as we know, like AI in healthcare has been improved like a lot along the years. But the thing is like these patient safety events, it's been documented in a very well-known systems, which is the traditional instant reporting systems at the IRS. So the whole process about the IRS, like what we want to learn from patient safety accidents is like first they identify when something happened, they identify the bad things, the adverse events, report them and investigate them, analyze, act. Hopefully we can learn from the patient safety or like events to prevent the future incident happens. But there are a lot of like limitations about the traditional incident reporting systems. So for example, this is most really on the retrospective approaches. So that means like only something happened, then you can document the adverse events. And also is challenging in analyze the large volumes of the incident reports, because like every year they submit like thousands, billions of reports just related to what things happen to patients in the healthcare. For our human like abilities is kind of limited for us to analyze them efficiently. Even when we have a very long and lengthy report, we maybe overlook some details that can be like very important for us to learn about like the action strategies that we can implement in the future crisis. And also the IRS has another disadvantage is like kind of underutilization of the worker generated self-reports. So we know the health provider side about the patient safety, but we also want to know like what the everyday healthcare like basis and how to improve the whole process of the patient safety activities. So that means like we have a large kind of like blind spot here. A lot of things happened during our daily healthcare like activities, but only like maybe 1 or 2% got reported in these IRS like systems. So we want to know like what the potential to learn about everyday patterns, about adaptations, the resilience of like performance and the capacity. So that's why we had the resilience engineering tool to improve patient safety, RETIPS. RETIPS is a semi-structured self-reporting tool during COVID-19. And this is just like the example about the RETIPS collections. And this is framework of how RETIPS can overcoming the challenges of IRS to traditional instant reporting systems to promote more proactive learning in healthcare systems. So like the RETIPS can fill a huge blind spot in the organizational learning by collecting the narratives of everyday successful and adaptive performance from frontline workers. So this is the questions we are gonna actually ask the healthcare frontline workers what their experience or recommendations about their everyday work to help us to reduce the patient adverse events. So this data can complement the instant reports like the adverse events about patients. But we have these research ideas. And things like the one big challenge about RETIPS is like we have a large volumes of data waiting for us to explore. And when compared to AI capabilities, the human is like really our hands are tied to submit to analyze like the billions reports submit every day. And this is the things we want the large language models. The AI can help us to overcome this challenge. But another challenge about RETIPS is like the upsides of the interview data, the service data we collected from the frontline workers are limited. Like it's hard for us to get like maybe thousands of reports, have a comprehensive idea about what their daily like in the front line healthcare. So large language models just can really in handy because it's a powerful generative artificial intelligence technology. It can generate coherent and contextual relevant content based on human authored prompts. And also previous research had indicated like this is a huge potential of large language models in analyze the healthcare worker self-reports. It can offer us the new potential abilities and opportunities to identify the adaptive patterns in the everyday work. Like we want to learn what we can continue to go or what we should avoid in the future. So the LLM can help us like learn at scale from the self-reports, which means the combination of RETIPS reports as well as the IRS reports to inform proactive learning in the healthcare. And this is our framework about this research. So with the help of large language models, which we can implement in the Palmetto 2 with the supercomputing power, and we want to integrate RETIPS and IRS, like the two opposite perspectives about patient safety to promote the proactive learning in healthcare. So the first project of our research is leverage the open source generative large language model, Llama, Meta Llama, to scale analysis of lessons learned from instance and RETIPS reports. And the further objective is like we want to compare human-generated and the LLM-generated labels between the IRS and RETIPS for the qualitative difference. We want to demonstrate the value of IRS and RETIPS as complementary learning tools to proactively identify the resilient performance and adaptive patterns in everyday work with the help of large language models. And just like one tip here is like large language models, like since it require a lot of like computing abilities, so it's hard for us to run with our laptop. Like the only way we run is with Palmetto 2. And here is the approach. This is just like how we collect data. We have the collections and we have the response from the frontline workers, and we have the instant tab to record like the hospital patient's instant report. So this is the real data will look like can help us to analyze any pattern of things for us to learn. And for here, why we have human-generated classification process is like large language models or AI, they are very good. They are very good of analyzing reports, but they have the limitation of hallucination, or like sometimes without human guidance, it can just like report like nonsense insights, or is not just like viable insights for to learn. So before we get the use of large language models, we will have human-generated classification process. So basic idea is like we have RETIPS reports 56. So in order to compare with the perspective of RETIPS reports, we also selected 56 reports from the instant reports. We have 2 human experts in human factors and healthcare to code them independently, and then we reconcile their codes, and then go to multiple rounds of iterative feedback about the codes and reconcile again. So finally, we will have the optimal healthcare generated labels for the 5 categories. So the 5 categories is about challenges, strategies, felicitors, and research and non-research that happens or mentioned in the reports, because these 5 themes is very important for us to learn how we can do proactive learning when something bad happens, or just to prevent like future adverse events. And with the hope of human-generated insights, so for this one, we will have 2 workflows of LLM, large language model generated classification process. So why we have 2 phases is because like for this text labeling part, we can use like prompt tuning techniques for us to improve the quality of LLM text labels, and with the categories of challenges, strategies, and facilitators. And for text like binary classification, we know the large language models and or the AI models like works really great when you have massive data. But since from the interview data, the RETIPS, we only have 56 reports. So we want to fine tune the large language models with data augmentation. So for us to learn the real scenarios from the reports as a training data set, augment the training data sets to help us to improve the classification accuracy. So with that being said, this is a detailed framework of how we prompt tune the large language models. And in our research, we use the Llama 317B. So you can see here. And so basically, we want the large language models to learn and to be trained only for our reports. So we will have instruction, a very detailed instruction about how to label these reports. And also we want the prompt engineering with a full shot learning. So remember, like we have human generated labels, right? We want to use human generated labels as examples. So for just to guide the large language model to think how to do the prompt, how to generate our labels and proactive like themes and patterns. So here we also have human experts to refine the prompt and to select the examples that we have human generated. And also we have like multiple rounds of quality check about outputs of large language models to give you or more sense about the prompt. So this is the prompt and we are gonna input to the large language models. We will have the definition about reports and the category definition and how we want the classification go, and we will have inputs and our output, and then we will finally after the quality check, we will finally have like to train the large language models to generate the themes and patterns we want to see to help us to learn like what's going on in the instance. And then for the binary text classification here, we use the pre-trained large language models, but also prompt tunes from the first phase. And for this one, we are doing different tags, which is data augmentation. So here we have like expand the 56 reports, the original data sets, to 300 reports. And after training, we also want to fine-tune models, the hyperparameters fine-tuning in the large language models, and use 3 different machine learning like models. And also, again, we have like human experts to do all the quality check to make sure the augmented reports like represents the qualitative representations from the original reports. And we also want to reduce like overfitting and underfitting. So we basically just like want to improve the classification accuracy to help us to get the synthetic like reports to get the results about research or non-research that involved that in the reports, so we can know like which research we should to get more for the next year, or which research maybe they don't have a very significant influence about how to reduce the patient incidence rate. With that being said, So with the help of Palmetto 2 and the LLM, the open source Llama model and the supercomputing power, finally I have the resource to make sure my dreams like become a reality. So here is just a reconcile classification and labeling source of humans. So basically we have two human coders, and this resource we have from the RETIPS and IRS. So here I just want to point out, like, since the IRS is more focused on what's in like going wrong in the incident reports, so they have like 9 themes of challenges, and the RETIPS is focused on what is normal, like what is normal healthcare activity like, and what goes where. So we have only 3 challenge reports. So these human-generated themes and patterns will help us to guide the large language models to learn. And this is the resource that we came from large language models. For the first part of text labeling, we want to know what challenges, strategies, and facilitators that involved in both reports. So from here, we can see, like, even though like there are like different same names, but they can share different same understanding between human and the large language model. So basically, large language model did a good job to analyzing these reports for resilient performance. But here we also can see the nuance that the large language models can capture. So for human, we only know like maybe, okay, there is strategies that worked to solve the patient's instance. Like we can notify the staff, but for large language models, like, yes, this is going to not to let the doctor know. So it's more kind of detail and nuance. And also for here, we want to know use resource supply orders, but from the large language models output, we can know, okay, this is involved like the test, the COVID-19 mask. This is kind of like detailed specific resource that we want to use. So in general, human get a kind of like generalize the resource from our training data sets, but LLM can capture more nuance or details, help us to learn more proactive insights for the active patterns. So here is a big potential for us to expand our data sets. So in that way, we can know like how large language models to help us like to understand what happens in their frontline like healthcare activities and what happens in the hospital with all the like powerful large language models we can have. And then this is part 2 of the resource. We have the synthetic reports, and actually the like kind of fake data is kind of like mimic the real scenarios in the RETIPS and in the IRS. So with all the like augmented data, and then we can use the 3 large language models to classify either the reports contain resource or non-resource. So we can see this large language model have the highest accuracy, and also this total average processing time per report. We can see the Llama model can like massively reduce the processing time, which like for human maybe we need to take like 7 more minutes to understand and analyze one report, but Llama can just like really help us to get all the reports like in a like less time. So in conclusion, so our contribution is like we compare like 2 different perspectives of reports, so that can give a very comprehensive proactive learning in the healthcare. And also for the generative AI tools, large language models, it can analyze and understand faster, and it had a reliable analysis of self-reports, and the use of large language models for text analysis and the data augmentation for our training data sets is good. And we also can know like for the large like volume of data, large language models can really scale up the learning for system level resilience purpose. And this is a framework of how we want to implement large language models for proactive learning in healthcare in the future. And limitation is like, because for interview data RETIPS, we only have 56 reports, so it's kind of small. So we want to explore more larger and diverse data sets. And the language restriction here, like we only choose English, like only reports. So in hospital, we know like some people, like different race, they can speak different language, such as Chinese or Spanish. We want to expand the reports to cover like more language, and also human oversight needs. So we have the results like for large language models without human oversight, without human guidance. And then that comes to LLM's hallucination. So we input one report for large language models to analyze it, and then output can be nonsense. So this is their kind of like biggest problem in the AI in healthcare. So for ours to overcome the hallucination as like possible as we can, and then we want to explore more powerful large language models, and with the hope of the HPC and or the kind of like the AI improvements, I hope we can make sure we can just like to overcome the limitations in the future. And that's it. If I have any question, please feel free to ask.
Fantastic. Thank you so much, Krystal. And thank you, Carl, for going over all the different workloads that you have. I do have a few questions for you, Krystal. So the first one is, so you've covered a ton of information here. I need to go back to the recording and try to gather everything. But to start with, did you get any surprising results, or was it fairly straightforward from your thesis to your results?
Mm-hmm. So as I say, like for our research here, we use the human guidance. Like we have the human insights for us to train the large language models. And back then, when we don't have the human generate the themes or labels or patterns, the output from the large language models is kind of like, it doesn't make sense. And things like generative model, sometimes they can generate the things that didn't happen in the report.
Yeah, the hallucinations that you were talking about.
Yeah.
So I know you talked about, so you got the slide open here. You're talking about fine-tuning and prompt tuning.
Yeah.
Can you explain that in layman's terms for people who might not be as technical when it comes to tuning LLMs?
Yes. So tuning is basically, we want to test this model. We have like a lot of like maybe 3 billion like parameters. Tuning is, we want to find the optimal parameter settings for the model in order for us to get better results. And prompt tuning is like, if you are using ChatGPT, and then you like the input is like prompt. So you give the instruction to the model to see, for example, summarize this report for me. So this is, we see the prompt. And prompt tuning is like how you can to give a very clear but also easy to understand prompt for the model easy to understand, then you can get better results. So prompt tuning is like, we want to tune the prompts, to try different prompts. Like maybe prompt A can give you result A and prompt B give result B. So like result A or B, like which one you think is better, then we will use the prompts. And for fine tuning is we want to prompt the parameters of large language models. And in that case, in our research, we fine tune the temperature of the model. So basically, temperature is a range from 0 to 1. And 0 means like the large language models can output a very conservative results. And 1, it means like the model can generate like the results very correctively. So we want to find like the optimal temperature from 0 to 1 to help us to understand our reports better. It's like only for our reports. And another parameters that we fine tune in our research is the number of arguments. So here we can see we have only 56 and we augment the reports for 300. But actually we don't need the all 300 reports for us to train the model. So for example, for this model, we maybe need only 100 arguments for the report. And then we will have our classification accuracy better, works better.
Fantastic. So looking at the results here, I think the results are very clear. We can get a better understanding of all the reports. I really love that you honed in on improving the nuance as well that you were talking about. Do you see this as being a possible way into having kind of like a feedback loop into improving healthcare?
Yes, definitely. Yes, I think this is very exciting point. When I get the results, so the feedback. Right now, the large language models we have transformer. The transformer infrastructure and the neural networks, and the one really can improve results is reinforcement learning with human feedback. So with the feedback loop, so for this research, we only have 2 human experts for us to give feedback about the results from LLM. But if we can do more rounds of the feedback loop, to make sure that the loop is more comprehensive, definitely the results is will really give you the most valuable insights that you really want to learn.
This is all fantastic. I am so glad that you were here and were able to be sharing all the information, all the results from your studies here. This is amazing. Thank you so much.
It's my pleasure. Thank you for having me.
I do have a question for you, Carl, as well. You were talking about a lot of new workloads that you're taking on, and you were talking about advanced manufacturing, biomedical data science and informatics, material science, cyber infrastructure, and intelligent transportation. What kind of workloads do you foresee will have in the near future? What kind of research are we going to do using the new AI infrastructure that you have?
Yeah, I think there are two sort of, 2 or 3 different ways to break that down. One is that I think every kind of researcher is going to be integrating more AI tools into their workflow, just as everybody in our society is going to be integrating more AI tools into their workflow. And so, there's a lot to be done to a lot of work for that Center for, Human AI Interaction that I referred to, a lot of work for them to do in figuring out how do we make that happen as smoothly as possible. But then, of course, there are the researchers who are actually doing research into AI or innovative ways of using AI. And there, I think the the field is so incredibly open and so wildly unpredictable at this point. Obviously, right now, a lot of people have their attention captured by, large language models, because those are what's, exploding so much these days. There's, obviously a lot to be done in terms of incorporating models like that, not just into text-related research, but also, we have researchers who are retraining large language models with structured representations of molecular structures. There's the so-called SMILE language for representing molecular structures, and you can train a large language model to work in that domain, even though it's not language. It's sufficiently language-like that these models can learn it very well. So I think there's a lot of work to be done like that, of figuring out where do the capabilities of these models begin and end? And that's again just thinking about the generative LLM style models, but at Clemson we have, as I said, just a ton of material science, a ton of biomedical work, a ton of computer vision and autonomous systems research that, yeah, I mean, to be more specific than that, I think I would have to pretend to be a more accurate foreteller than I am. So maybe I'll leave it there.
Yeah, that sounds good. Yeah, I agree. The AI space has just grown exponentially within the past couple of years, and it continues to grow exponentially. And the use cases for it is changing by every week, essentially. And yeah, we're just seeing more and more. So I think that was a great answer. Thank you, everyone. Thank you, Carl. Thank you, Krystal. Thank you, Becky, Scott, Thomas. Thank you all for being here for this webinar, and thank you everyone that has been on listening and watching the webinar here. As we say goodbye to the audience, is there anything that you would like to share, any new and interesting things that you would like to share with the audience, or where to get more information about the work that you're doing?
We have a lot of documentation and information online about RCD, about the Research Computing and Data Group. So I invite people to Google if they're interested. They can read, a lot of the interesting stuff that Scott talked about the structure of the cluster is there, and the services we provide, and other things about AI research happening at Clemson.
Fantastic. Well, thank you, everyone. And I'm going to say goodbye to the audience, and we'll see you soon at another webinar here in the Cosmos community. Thank you all.
Thank you.